Okay, hello everyone. So next in our series of webinars, just a couple of points for anyone who hasn't attended any of the previous ones. The slides for this event are now directly linked from the events entry on the Astrobiology website. So if you are watching this at a later date or you're only dialed in to the telecom, you can pull down the slides and work along with us. The video for this will be up probably in about a week's time. As we're going through the webinar, by all means, pop your questions or thoughts into the text chat window down at the bottom. Everything is being recorded, just so you know, so we've got audio and what you're typing in with attribution. And then at the end, after the presentations, we'll open up the phone lines and have the conversation around that. Okay? Sure.
Thank you, Andy, and thanks, Estelle, for making all this possible. And I'd also like to thank Doctors Ty Robinson and Nancy King, who are hanging on the line there in case there are any questions, and I'm sure there will be that I can't answer, or if they want to mention something that I forgot to mention. Today's topic is how can we identify habitable planets and search for life beyond our solar system. This follows on yesterday's presentation pretty directly. Yesterday, I don't remember the exact wording, but it was something like how can we identify habitable environments inside the solar system. And so this is sort of integrating that over a sphere, a globe, and looking at that sphere from far, far away. In other words, for planets around other stars as opposed to planets in our own solar system. And that mostly means remote detection of both habitability and life. We're going to follow this same sort of nucleus of people with a third, actually the fourth telecon after the new year that parrots the second part of this, which is the search for life inside the solar system. So we did the search for habitable environments inside the solar system yesterday. Today we're doing the search for habitable planets and the search for life beyond the solar system. And in a few months, because we're still working on the document, we'll do a search for life inside the solar system white paper. And the reason that we've smushed the two together for exoplanets, for the search for life in habitable environments together outside the solar system, is that the techniques are really similar and a lot of the driving questions are very interrelated, as we're going to see today. One other just housekeeping note, the format I'm presenting with today and the format of our document is a new template that Michael New gave me last Friday that we're trying to implement. So we're sort of the lab rats for that, or lab microbes, as most in our community tend to work with smaller organisms as opposed to the macroorganisms. But if you want to take a look at this and implement it yourselves, feel free to do so. I found it pretty useful. It follows on the templates that a couple of the groups have been using the last 2 weeks that both the authors and the community have seemed to enjoy. So hopefully this goes well, and if it doesn't, let us know. So with that said, on to our presentation. This is fortunate and unfortunate timing in many ways. I think it's unfortunate because we have lots of people either in California physically at NASA Ames or remotely tuning in to the meeting that's going on there right now, which is the second Kepler Science Conference. And on Monday at that conference, there was an associated press release and press telecon about this announcement, about an estimation of how many potentially habitable worlds there are in our galaxy. And the answer is in the tens of billions. Now, there are people in the exoplanet community, and I would actually say that most of the astrobiologists that populate the exoplanet community have some issues with the press conference or the paper with the exact percentage of stars that might have these potentially habitable worlds. But the big picture number is still the same, or the qualitative conclusion is still the same. There's lots of potentially habitable worlds out there. They say 40 billion. Even people that might be a little bit more skeptical might put the number at 10 billion. But at some point, you don't need many more habitable planets. It'll affect telescope design and stuff like that. But the big news here is really sound. There's a lot of habitable planets out there that we want to explore. And so that leads us to the questions we'd like to answer over the next 10 years. Are they habitable? And if they are habitable, do they have life? And a lot of this text that you're going to see here is just copied and pasted from our document. So if you see yourself reacting to this in a way that makes you think we forgot something or makes you think we said something that's incorrect, please speak up and let us know because we need to get that into the document. That's what this telecon is all about. So the introduction, I'm just going to paraphrase a bit. Exoplanetary science, so it's science about stars, planets around other stars. It's rapidly growing, in part because our data set is rapidly growing, and it's evolving. In the near future, we may be asked to prioritize these habitable planets that we're finding for targeted follow-up observations, which is a lot what we'll talk about today. Those data will provide limited glimpses into the atmospheric and surface environments of those exoplanets and allow us to constrain the likelihood of surface liquid water and or life. Liquid water being the main thing that we use to discriminate potentially habitable versus not potentially habitable worlds, and life being the thing that astrobiology is ultimately after in the long run. With the accelerating rate of discovery of exoplanets, we want to be able to target for observations those planets most likely to harbor liquid water and hence potentially life. So this is the first thing other than the title that you'll see in the template that we applied. And this is just a summary of sort of where we're at. This is also from that Kepler meeting. I'm going to mute that music. And this is called the Kepler Orrery 3. It's in Roman numeral 3 if you want to look for this in yourself or use it in a talk. This is a slide summarizing all of the Kepler objects of interest. And if you hear KOI from that team, that's what that represents. This is all the planets or planet candidates that the Kepler mission has found. And there are literally thousands of them. Many of them are terrestrial sized, many of them are in the habitable zone, and many of them are both terrestrial sized and in the habitable zone. And the question is, how do we prioritize amongst all of these for future observations when we want to look for life? And one of those big prioritizations is going to be detectability, which we're not going to talk a lot about today. We're going to talk more about the astrobiology science of the other criterion for prioritization, which is how likely is that planet to harbor life, or at least to have the potential to harbor life. So this is the next part of the template, which is background, just a couple paragraphs saying, what is this all about and why is it related to astrobiology? A habitable and I just took the topic sentences from those paragraphs. So what this is all about is that a habitable planet is typically or traditionally defined as a world able to maintain liquid water on its surface. And if you hear the words habitable zone, that's generally what we're talking about. If you hear Earth-like, potentially Earth-like, that's generally what people are referring to. Information provided by current exoplanet detection techniques and available or near future instrumentation can begin to address the likelihood that a certain exoplanet is habitable. So then the next thing you'll see in the template and in our document is a splitting up into subtopics. You don't have to do this. We found it useful because we're ultimately addressing two questions. The first about habitability and the second about life. And so for us, you'll see subtopic A, characterizing potentially habitable exoplanets. And then you'll see a subtopic B on the search for life on those potentially habitable exoplanets. And these are just a few of the bullets from our subtopic A explanation, which is in prose form on the main document. Planet origins, we want to know more about how they form, which was a white paper we saw a couple weeks ago, maybe a week ago. Composition of the interstellar medium, accretion processes, and orbital evolution. So this is all about how the bulk planet forms. What is it made of? Where is it located with regards to its star? And does it have the elements and ideally the molecules that life needs? And the next bullet here is planet and system configuration. What's the star type? What is the stellar planetary system environment? What is the planet's mass and the planet's size? What are its orbital parameters and what is its composition? So this is once you form that planet, actually looking at it. How big is it? If it's too big, it might collapse a gas envelope around it and be more like Jupiter. And you might hypothesize about floaters or something like that living there. I think that's A, less likely, and B, if it is, those types of organisms do exist, they're going to be I think, a lot harder to detect spectroscopically from far away, which is something we'll get to later on in this presentation. Conversely, if a planet is too small, like the moon, I think is a great example of this. The moon is a rocky planet smack dab in the middle of the habitable zone, right? It gets just as much energy from its parent star, the sun, as we get from our parent star, the sun. But it's far too small to hold an atmosphere, so it's not habitable. And that's why it's not habitable. If the moon were the size of the Earth and we lived in a true binary planet system, the moon could potentially be habitable, right? But it's not. So size matters when it comes to exoplanets. The stellar properties also matter. It matters because that defines how far out you have to be from that star to get the right amount of energy to maintain liquid water. It also matters because the distribution of energy from short wavelength UV photons to longer wavelength visible and infrared photons really affects the chemistry of the atmosphere. And that in turn can affect both the habitability of the planet, because it's those atmospheric chemicals that are causing the greenhouse effect that maintain habitability, and it can affect the biosignatures, because the biosignatures, for the most part, are ultimately going to be gaseous. Although Nancy has some great ideas on non-gaseous biosignatures that we'll hopefully talk about later. Finally, planet evolution. The ability to maintain liquid surface water and a habitability factor through time. I've talked about the surface water quite a bit. And I should say, let me pause here for a second. We use the word habitable zone, and that can be controversial within the planetary sciences community, because those folks know of planets like Europa that are clearly habitable, even though it's well outside the habitable zone. Same thing with Titan and Enceladus and pretty much any proposed outer solar system abode for life. It also has been controversial within the exoplanet community, because they want us to think outside the box when it comes to looking for life. There have been proposals of dry planets that might have an expanded habitable zone, or hydrogen-dominated atmospheres that might maintain liquid water oceans far, far away from the star and outside the classical or canonical or casting habitable zone. And I think that there might be room for a discussion about a better term than habitable zone, because what we're really referring to there is a specific type of habitability that allows us to probe that planet from life from far away. And what that really means is a planet that has or can maintain a large enough biosphere to produce a very large atmospheric, or at least spectroscopic signature that can be seen through all the noise provided by the star, because the star is much brighter than the planet. So the planet's biosphere better be producing a whopping big signature if we're going to be able to see it from far away against the background of the star and all of the things that the planet is doing that aren't biology. So that's why we have focused on liquid water. It's not because we're excluding other kinds of life. It's because we know how to detect that, and it's going to be, frankly, a lot easier to detect, even if we had some theoretical way to detect non-water-based life or non-surface biospheres. The habitability factor is basically a quantitative means of assessing the likelihood that a planet has liquid water, and if we want to go beyond liquid water, which I think we should get to, also those factors as well. So habitability factor, you could imagine it as integrating over all the parameter space of a particular planet and assessing the likelihood that that planet has life, or at least has the conditions amenable to life. Okay, so here are some sub-questions on subtopic A. So this would be the next thing. In each subtopic, you'll have an explanation, and then you'll have the sub-questions for that subtopic. So one is, how can we improve characterization methods so as not to miss detection of surface liquid water? So this is, we don't want to have a false negative. We don't want to look at a planet, say it doesn't have water, and in fact it does, because that might be one of our better planets to do follow-up observations of. Can we define a habitability factor, which is something I just discussed, that encompasses planetary characteristics and planet-star and planetary system interactions to inform the relatively likelihood, you might need to rephrase that the planet is habitable. So this is all about, again, that sort of quantitative assessment, incorporating as much as we possibly can into whether or not a planet can potentially harbor a global detectable biosphere. Lastly, what are the potential extensions to the habitable zone? Are they associated with different habitability signatures and different biosignatures? So this is where we start to blend the two together. People are talking about a dune planet that's really dry and that suppresses some of the positive feedback loops involving water that can cause a planet to freeze over or to steam away. If that planet is habitable, maybe it has a different type of biosignature than a wet planet like modern Earth has. Likewise, if a planet has a hydrogen-dominated biosphere, does it have different biosignatures? There's actually, I think, a really nice paper by Sarah Seeger about this a couple of weeks ago. I think it was in AppJ, but I'm forgetting exactly where it appeared. You can look it up, Google it. But these are the types of questions we want to answer. Not just is a planet habitable, but what do the constraints on habitability mean for the biosignatures? And that's where subtopic A and subtopic B start to meet. So subtopic B is about that search for life. Detecting the presence of life on an extrasolar, and so now we're back at the explanation part of the subtopic. Detecting the presence of life on an extrasolar planet requires understanding life's global impact on its environment for a variety of different energy metabolisms in planetary environments. And I'm going to define metabolisms at the end here. We mean something specific, which isn't always what biologists mean. We mean sort of the net chemical reaction that life does, or the net chemical reactions life do, not all of the network of reactions that occur inside a cell. And that causes confusion sometimes. So like, for example, metabolisms, we mean methanogenesis or oxygenic photosynthesis or nitrogen fixation. We want to know the process that the biota or the ecosystem is imparting onto the atmosphere and onto its external environment. What's going on inside the cell, I shouldn't say we don't care about it, because we care a great deal about it. But for the most part, in our models and in our considerations, it's a black box. And so long as the biologists are understanding and characterizing that black box accurately and as completely as possible, then we're quite happy with it. Although, you know, other people might might have different opinions on that. But that's sort of my take. The search for life, whether in situ or remote, requires prioritization. In other words, literally in a world, in a galaxy with 10 billion extrasolar planets that might be habitable, which ones do you look at first? So the sub-questions for subtopic B: metabolism, environment connections, how to improve understanding and prioritize targets. So that's what I was just referring to. Detectability: what's the most easily observable biosignatures? If ozone and oxygen and methane, which are sort of the traditional ones, if they're the most easily observable ones or the most characterized ones, then those are two or three of the ones that we're going to look at first. And we also have to keep in mind technology, right? There are some great proposals for biosignatures out there, and ones that have been used to I think, pretty good success here on Earth, and either are being used or will be used on the near term in Mars. Isotopic fractionation is a great example, and maybe one day they'll be used in other solar system targets. But a lot of those signatures aren't going to be capable of being applied to these remote observations, especially when you get into like iron isotope fractionation. You're just not going to be able to apply that to an extrasolar planet until we get enough money and fuel to send a probe there. And that, I definitely don't plan on being alive that long. And I definitely don't plan on being alive long enough for the probe to reach the planet. Robust combination of wavelength ranges and spectral features to target. Because keep in mind, pretty much until we send that probe, all we're getting is a spectrum, different colors of light, and we're analyzing those different colors to find out what chemicals are in the atmosphere, what's on the surface, and what those two things mean for the presence of life on the planet. And then lastly, a topic near and dear to my own heart: false positives and false negatives. We need to look at all the possibilities for a living planet to make us think that it is dead because it doesn't have the biosignatures that we're looking for. And we also want to avoid the case where a dead planet has geological or other non-biological processes that generate either the gases that we're looking for. So you could imagine a planet that generates oxygen or ozone or methane that imparts that signature onto the atmosphere, and also the possibility that that planet could generate other gases that happen to have a similar absorption feature, especially when our first observations aren't going to have an extremely high resolution spectral resolution. So in other words, if you've got two gases, oxygen, and I can't think of another example off the top of my head, and they absorb at the same wavelength of light, the measurement you're making is absorption at that wavelength of light. And if you've got that other gas, that non-biosignature gas in the atmosphere, it could, for all the purposes that we're using it for, look like the biosignature. And so we want to at least be capable of understanding those, so we have ways to discriminate between the false positives and the true positives. Okay, so things to work on in the coming 10 years. I've probably talked about a lot of this already. We want this quantitative habitability factor. Given that habitability factor, we want the biosignatures for that specific planet, given the constraints from the habitability assessment. We want a comprehensive catalog of biosignatures, as well as the false positives and negatives for those biosignatures and for those biospheres. Starlight suppression technology. So we haven't talked a lot about technology, and in general, we're avoiding that in the roadmap. We put this one bullet point in here because it's so critical. We need better starlight suppression technology so we can directly image these planets. That's going to be the best way to get the data that we want to assess habitability and to assess the presence of life. Otherwise, there's almost no way to do it. We can do it with transit spectroscopy. That's only going to probe the upper parts of the atmosphere. And so this is one of those fields where you sort of have this one tall pole technology-wise that is going to hold all of our other research up for quite some time, in my opinion. Everything else is going to be theoretical until we get the starlight suppression down to about, usually the number is like 10 to the 10th. So basically we have to suppress the starlight by a factor of 10 to the 10th more than we suppress the light coming from the planet light. And that'll let us image the planet and then do all the wonderful things we're talking about in this presentation. Understanding the information content of planetary spectra, including methods to retrieve or infer surface properties relevant to habitability, particularly surface liquid water. So we'd like to have some way to not just have a spectrum come in and say, oh, that looks like it has oxygen and that looks like it has carbon dioxide. We'd like to have some rigorous and robust methodology that will do that as the data come in, because otherwise we might be imposing our own hypotheses on that planet onto our analyses. And lastly, comparative climatology. Are super Earths inhabitable, or are they habitable? Are they inhabited? These are the types of things we can get at if we've got good models that can simulate not just Earth, but also Mars and Venus and ideally the gas giants, Titan, and the entire history of those planets. Because if we have a model that can do these things, we have more confidence that it can do sort of the in-between planets, right? If you've got a model that can do Earth and it can also do a gas giant, well, you have a little bit more confidence that it can do the in-between cases of super-Earth planets than you would if the model was just validated against Earth. And the other thing we need in terms of comparative climatology is not just comparing one model's results on different planets, but also comparing different models on the same planet, right? This is something that Earth scientists have done very successfully in the IPCC, the Intergovernmental Panel on Climate Change, for well over a decade now. And I think we need to take their lead and start comparing our different models for terrestrial planets inside and beyond our solar system, so we better understand the uncertainties in all these different models, the uncertainties as a suite of models, and so that we can start understanding which parts of which models seem to perform the best. And then once you start doing that, you can start, swapping code a little bit. And there's danger there because sometimes that means you're all using each other's code to the point where all the models become homogeneous, which is a problem sometimes in the earth sciences community, and that's something we need to be cognizant of. But the brighter side of that is the best code in the long run will win out. And so we'll have, and if we keep innovating and coming up with new ideas, especially for the weak points like clouds or whatnot, that'll improve our community in the long run. Okay, so connections to other questions. This is, again, the next, and I should say, if you see something big up in the topic part of these slides, that's another step in the template, another top header line in the template. So connections to other questions. These are the ones I just pulled off of the document. How do we remotely find and identify an inhabited planet so that there's obvious connections there? How can a world generate and support life, and how can we use remote characterization to understand such worlds? Again, that's a lot of the techniques we've been discussing today. How do habitable planetary systems form? That's sort of how did the planets get there? And it also helps to some degree because it's similar tools to analyzing the planet-planet interaction parts of habitability. It also can impact the habitable history of that planet. So Rory Barnes and Brian Jackson have done some interesting work about planets that may be in a habitable zone now, but and actually Stephen Kane and some other people out in California have done this, where you have systems that may be habitable now, but have had parts of their histories where they had gone through uninhabitable phase space. And you'd like to identify those ahead of time if you can. And it's the same tools as the how do habitable planetary systems form people use. At least subsets of both tools are the same. What is the applicability of our geophysical knowledge of Earth to rocky exoplanets? Personally, this isn't an area of research that I pursue, but I have always maintained that this is one of our biggest unknowns when it comes to exoplanet research. How important is it to have any kind of tectonics, whether it's plate tectonics like we have on Earth, or some sort of lid or overturned tectonics like we have on Venus, or pipe volcanism like we have on Io? First of all, how important is tectonics? Question mark. What controls whether or not a planet has tectonics? What do the different types of tectonic regimes imply for habitability? And what controls that? What controls whether you're plate, overturn, or pipe volcanism, right? People have started to look at this just over the last decade, but I think that research is still pretty new, and I think there's a lot of room to improve on that. And it's not because people haven't done good work. They've done excellent work, but we're just getting started as a community. How can we enhance the utility of biosignatures? That's obvious, right? If we're going to look for life, we want to make sure that these biosignatures are robust. How does the evolution of the atmosphere and its interactions with the solid Earth and biosphere inform our exploration of habitable worlds? And this is similar to the thing I said a couple points above, right? Like, you want to know how the mantle, the redox state of the mantle, the chemical composition of the mantle affects the atmosphere. You'd also like to know the opposite. How does the carbonate silicate feedback cycle work in a very generic sense? Are there other carbonate silicate-like feedback cycles, then that's the mechanism by which the lithosphere, the rocky part of the Earth, has sort of acted as a thermostat over long time periods to keep Earth's surface habitable. Are there other versions of that apply to exoplanets with different rock composition or different atmospheric composition? These are the types of things I'd like to hear a lot more people doing research on.
John, I just want to jump in
there.
I just want to jump in and note these questions are all explored in more detail in the other white paper docs. So these are just the headlines for those documents.
Right. I'm trying to, I guess, just describe the relationship between this and them, and then highlighting the areas where I think there's particular relevancy, and especially when it's not obvious. How can we understand Earth's past, present, and future as proxies for habitable worlds? This is an area of work where I think it's particularly related to the false positives and false negatives. If you want to look at a weird biosphere, in my mind, the best place to go is early Earth, when the biosphere was weird, and yet we know it existed and we know it worked, because there's lots of rock data that are telling us all those things. And what's more, because the rock data are there, we can do the scientific method. We can propose hypotheses for how that biosphere worked at that time and test them with further examinations of the rock record. And all of those lessons are going to be applied to exoplanets, because if you have a different biosphere, you know it worked, you want to examine it in great detail. I always say that early Earth is the best and most complete record of an alien biosphere that we have. And how can we identify habitable environments in the solar system? The lessons we learn by searching for habitable environments and searching for life, whether it's on early Earth or other planets, are always going to be applicable to our search elsewhere. I think the case of false positives and false negatives has tremendous analogs and parallel stories in our search for the earliest life on Earth and in our search for life on other planets. And we could go into long detail about that, but I should be quiet soon so Nancy and Ty and everyone else can talk. Okay, then there's a glossary, and I promised the definition of metabolism. There it is. I also define the habitable zone because I want to be explicit about what we mean in this sort of subsection of the community when we talk about habitability. And that's not to mean that we're right and everyone else is wrong. This is just how the term is historically used. And I think if people want to have a discussion about a new term that explains the same phenomenon, I think that can be healthy. But for context, this is the way it's been used in the past. And if you see it in the literature, this is how it has been used. And metabolism, again, when we say metabolism, we're looking at what goes into an organism and what comes out of an organism on a chemical basis. We're not worried about all of the reactions occurring inside the organism. Oh, and I had evolution there. I meant to define evolution. This is something else that often can cause some cross-field confusion. We don't always mean Darwinian or Lamarckian or any other kind of biological evolution on how organisms evolve over time within a biosphere. We're talking about change over time, just delta property, delta T. Okay, so evolution of a planet, you can have an evolution of a biosphere, you can have evolution of organisms. When we use evolution, we don't mean the specific process that Darwin wrote about so many years ago. We don't have any references yet, so this is blank, but I wanted to include it so people got a feel for what the new template looked like. And then I think this is the last slide that's part of the template. The authors, I've been talking and running over Nancy and Ty, so I apologize for that, but Nancy and Ty have done a lot of great work on this. Ty in particular really got the document into shape over the past weekend. Brittany Schmidt and Steve Vance and Robin Wordsworth and Dave Demarais and Roger Brockman and Vicki Meadows are all part of the larger group that's done this series of 4 webinars, of which this is the 3rd, on habitability and the search for life inside and beyond the solar system. I should say that Brittany and Steve really did great work on the very front end of that, getting us organized and splitting a monster document that we had up into the 3 or 4 documents that we're now presenting. So this really is a team effort. It's been almost all my words so far, but not even close to all my work. It's probably almost the opposite. So with that, I'm going to leave you to our last slide, which is just an encouragement to check out the document. I don't intend you to read this or to even be able to make out the individual characters on your screen. This is just to show you that there still is a lot more material we have not discussed today that's in the document. And so I encourage you to go and take a look at that document and see if we've missed anything or gotten anything wrong. So we look forward to your feedback, I guess, starting now, if anyone has any questions.
Well, could I suggest that, first of all, do you want to address any of the questions that have been coming up in the chat box? Because I can see Nancy and Ty have been typing away. Are there things that are worth expanding upon right now?
I would say let's leave that. Ty, Nancy, why don't you guys start there? I have not been able to see the questions. I'm going to stop sharing my screen.
Hey, Sean, I'm going to send the chat transcript to you, Nancy, and Ty. It's easier to read in email, but that'll go on in parallel.
But Nancy, Ty, do you two want to take over? And because I haven't been able to see these questions.
Ty,
sure.
Note down what questions are in the chat. So Glenn Chiolik, I don't know how to pronounce your name, a couple of us wanted to discuss what potentially habitable environments are we going to miss because of prioritization for detection methods? That's one question. There's Dave DeMurray made a suggestion that one habitability factor may be too restrictive, so maybe we might want to come up with a habitability profile instead. And I think John Rummel was noting on intelligent life being also offering biosignatures. So those are three prominent questions that came up in the chat.
Okay. Unless there's anything else you want to say on that, let me encourage our participants. The telephone lines are open. If you want, what we've done in the past is you can click the little hand icon, as you'll see it then appears next to my name, and we know you want to speak. Or if you feel overwhelmingly enthusiastic and just want to start talking now, go right ahead.
Well, let me respond to one of the things I just heard, which is this idea of a sort of a habitability, what was the term?
Profile.
Okay, so I think that's a great idea. And one thing I want to be explicit about is I didn't mean to say, we should get together as a community and come up with one algorithm or one equation to define the habitability factor. I probably should have said habitability factors, plural. And by making it singular, I've actually ignored something that Abel Mendez has been doing with coworkers, which is he's been coming up with quite a few different, I would say qualitative or semi-quantitative assessments of potential habitability of exoplanets. And I think that's a great start. I think we need multiple approaches, and the more approaches we have, the more our collective capability is going to be. So you might have one habitability factor that's really tuned towards how similar the planet is to Earth in terms of its potential to have a modern Earth biosphere. But you might have another that is a little bit more aggressive and a little bit more optimistic, if you want to use optimistic, pessimistic terms, in terms of the hydrogen-dominated biospheres or dry biospheres or things like that. So there might be different approaches. And you might end up having some catalog of what makes the planet habitable or uninhabitable, as Dave suggested. So I think multiple approaches are good because the different approaches are going to be used for different things. Some of them are going to be used for prioritization. Some of them are going to be used for real science, where we're trying to classify these things, do a taxonomy of exoplanets. That's something else Abel has started to do. So I think different approaches are good.
And on the subject of what Dave said, Dave, talk to us.
Yeah, well, now that you guys have found all this huge potential for habitable planets or potentially habitable planets, you're in the same situation that the Mars program was when we found water all over the place, or evidence of it. And that is you've got an embarrassment of riches, and as you rightly pointed out, you're going to have to figure out how to prioritize amongst those riches. And the historical precedent for this is site selection for landing the Curiosity rover, and the incredible exercise that we went through in doing that. And I guess where I'm coming from here is that there were 4 sites in the end that all just looked wonderful. They had evidence of flowing water, evidence that you could get deposits that were involved, and on and on and on. And if you come up and you addressed this, saying that your habitability factor, if you just came up with a single number that would have rated those, they would have all been the same. But by considering all the criteria that we consider important for a site, the thing that really made Gale Crater jump out in front of the others was this accessibility of a long record of deposits during a key period in early Mars history where climate change was really big deal. And that tent pole got so tall compared to the others that Gale prevailed. And so I'm just saying that in your exoplanet profiles or factors, whatever, that you allow the visibility into what could turn out to be an unanticipated tall tent pole that would pretty much trump a lot of the other things that otherwise would have given you also positive factors. So just making sure you have enough resolution, but also that people think about the different apples, oranges, and peaches that go into assessing habitability, preparing yourself for that star player that suddenly comes out of the pack. So that's
well. To expand on your analogy a little bit, Dave, one of the other things that seems to be taken into account, and I wasn't a part of this like you were, but is the other types of science one can do at a site. And I think the same thing would apply to an exoplanet. If you've got an exoplanet that has interesting non-astrobiological science to be done in that system, you might prioritize that over an equally interesting astrobiological target that is maybe less interesting for non-astrobiological but exoplanetary science purposes. And the other, just to go a little bit back on your analogy, I think maybe not the last decade or two, but maybe like the 1950s or 1960s pre-Viking might be a better analogy, just because we don't have the embarrassment of riches of data that the Mars community has for site selection, right? We have very limited data on these exoplanets, which is one of the reasons that prioritization is so difficult. We generally know how big they are. Hopefully we know the mass and the radius. Usually we only know one or the other. We know how far away it is. We know where to point the telescope. We know how far it is from its star and how much energy it gets. And if we have mass and radius and we're lucky in that way, we can make some guesses about composition and density and things, bulk composition and density. But chances are we're not going to have a lot of information, and not nearly as much as the Mars community has when it comes to site selection.
So you're sort of at the same stage as the Mars program was when we were figuring out what instruments to put on the first mapping orbiters. And that is to say, what are the list of measurements that need to be done to allow you the input to your habitability factor or whatever. But the key thing is it's a short list of observations. And so the value of thinking about a factor is that you're narrowing the list of all the darn things you might want to observe to a smaller, more tractable list that you could actually apply to a large number of targets. And so maybe you're sort of in that period where the Mars program was, where you're arguing about the types of orbiters to send in order to get to that next level of information.
So I just put up a link, and the link is to the PBS NewsHour on Tuesday. And basically, it's Jeff Marcy talking about the Kepler results. And at the end, he makes a very good point with respect to how SETI fits into all of this. I don't know in the current roadmap where SETI shows up, if at all, but I do think that there ought to be a place where it can be hooked in, because it is a technique that could, of course, transform our understanding, or at least our evidence for life elsewhere, and potential for intelligent life is really a real estate question. Is anybody out there? Do we already own it all? But I think that it ought to be kept in at some point, and I invite you to watch the PBS NewsHour and see what you think.
That was John? Was that John speaking?
Yeah.
I'll put out a related question. Are artificial kinds of biogenic gases detectable on our Earth as biosignatures, like industrial pollutants? Should we look for those too?
Yeah, I do think that it's a lot easier to envision detecting things that don't have to want to be detected or haven't developed their own NSA problems. But I do also think that it's an approach that is legitimate, and one that ought to be pursued at some, low level of effort.
So the approach that I, at least right now, have is when we find a planet that has life on it, in my mind, that's the point to really focus on SETI-type efforts on that object. Now, there's one exception to that. A lot of the Kepler planets, and this might have been part of what Jeff Marcy was referring to, a lot of the Kepler objects are too far away to do any detailed follow-up observation with direct imaging and characterization. So even if we got a flagship level telescope that can block out the light of a parent star so that we can see the planet, even if we got that, for many of the Kepler planets specifically, we would not be able to see the planet because they're too far away. We're only going to be able to see and directly image the planets that are closer to us. For those planets that are in the habitable zone and are of the right size to be habitable, the next step scientifically to probe those planets for life is SETI, is to listen for radio transmissions or something like that. That's the only thing you can do next, other than maybe if you can get some spectroscopic, some transit spectroscopy, you might be able to get something out of that. But absent a new mission or a new technique that I haven't seen mentioned by people, that's sort of the next step. Okay, so that's one place SETI can play a role. And the other is something similar to what was just discussed, which is sort of piggybacking. If you're looking at a planet, as Nancy suggested, and you're looking for oxygen and methane and ozone, and clearly industrial, non-natural, non-biological, non-geological gas pops up in your spectrum with a very clear, distinguishable feature, now that's something that's interesting, and interesting with regards to intelligence. I think there's also the possibility that if a EDI exists, if an extraterrestrial society existed and they lived in the right system, they also might choose to alter the climate of planets in that system to suit themselves. And the only reason I mention that is that's going to be a bigger signature on the atmosphere because they're so dramatically altering the climate than a pollution signature would be. Pollution signature, because if it's pollution, you generally don't want to keep doing it forever, and so it's going to be short-lived. So we'd have to get the right timing on an astronomical timescale to see it. And generally, they don't affect the climate radiation budget too much, and so they don't have large features. And unless we have a super high-resolution telescope in terms of wavelength, the wave number, we're not going to be able to detect them. If you're going to see an extraterrestrial intelligence, chances are they're going to be having some huge effect on the radiative transfer budget of the atmosphere. The most likely case is that they're altering the climate of another planet. Now, I don't think that that's particularly likely that we're going to see that, but I think, or let me rephrase, it's not the most likely, that's the most detectable case. That's a better way to phrase it. I don't think it's very likely, but at least if that was happening, it would be more easily detectable. But you get it for free.
Well, yeah. So I don't disagree with your general concepts, but I do think that it's important that we adopt the principle that the highest priority science isn't the only thing that gets funded. Otherwise, we would stop looking until we had that sunlight suppression technology that you had called for earlier. There are many different ways to go about this. When people were first starting to look for exoplanets, it was considered that, if you didn't have specific kinds of telescopes, you'd never be able to deal with this. But in fact, the way that planets were getting detected from the Earth's surface was completely different than what everybody said you had to have in the way of a mission. And so I think it's important to consider the effort as a legitimate one, not worry about sinking a whole lot of money into it. We're already going to build a square kilometer array, whether we like it or not. I mean, it doesn't really address these issues specifically. And just, keep it in as something that has the continuity so that you don't leave it on the cutting room floor in a way that is essentially intellectually not justified. So monetarily, we paid a bunch for SETI over the years, but by comparison to anything we've done in the International Space Station or any other space mission, it's been a chump change.
And just to emphasize that point, everything that I discussed and that Nancy mentioned at this point is more or less theoretical. I don't think we've done as nearly a thorough of a job looking at the potential industrial civilization biosignatures or technosignatures as we have for more generic biosignatures. And the reason is we're prioritizing the biosignatures. But you're right, we don't want to prioritize them to the exclusion of these other things that we might one day see, especially when the big cost, which is the mission, is the same, because you can run the same mission the same mission will give you both data sets. So I completely agree. We don't want to prioritize one thing to the exclusion of the other.
It's pretty nice to have all those planets to look at.
Sorry, are there other topics, other directions that the authors should be thinking about? What else might we suggest to help them strengthen their paper?
Dave Demery liked the idea of the glossary a lot.
And we're trying to highlight two things in the glossary. One is terms that might not be common in other fields, and the other is, and potentially worse, words that are common and used differently in other fields.
Does anybody want to suggest other terms besides the ones Sean put up? Or email us if you figure out some.
Or comment on the document.
Okay.
And Dave also had a suggestion to include the techno-signatures in the document, which Nancy said that we would, and I agree, we should.
The document will be switched over to comment mode as soon as this webinar is finished. And just in case anyone hasn't done this before, all you do is you highlight a piece of text, right-click and choose comment, and you can stick the equivalent of a post-it note on the edge of the document for that. Any other questions, any other points that people want to raise around this topic?
Yeah, I'll chime in. This is Steve Vance. Hi. Dave made this point about the embarrassment of riches relative to Mars. And then Sean, you responded saying, well, maybe the embarrassment of riches is a little more meager than that. The parallel that I draw is where we were with regard to observations of the outer solar system in the early 70s when infrared spectroscopy was just coming online. And then, we knew there are a lot of objects out there, and we were just beginning to see transits and to be able to look at atmospheric compositions. I'm excited that, the intervening 40 years have allowed us to get increasingly more detailed information and even to spatially resolve some of these features. So it's very analogous to exoplanet discovery. And I'm happy that there's a possibility that those fields will kind of move together and ask some of the same questions down the road.
I totally agree. I think that's a great analogy. And one thing that we didn't talk about is I think there's some room, and I've seen Dave Spiegel mention this in a Facebook conversation. I've had conversations with Brittany Schmidt about this in car rides around DC, is the possibility to look at solar system objects, and in particular the outer solar system objects, as analogs for exoplanets. One question that I don't think we've adequately addressed is, and I mentioned this in yesterday's webinar, is whether or not a giant icy world could have a remotely detectable gaseous biosignature. So imagine, if we can coin the term super Europa, a planet like Europa but the size of Earth, that has enough mass and gravity to hold onto and retain an atmosphere. Is there enough communication between the subsurface and the atmosphere of that planet for the atmosphere to accumulate a biosignature from the subsurface? We often assume Europa is not, if it has life, that life wouldn't be detectable across interstellar space. I totally agree with that assessment. If there was a true Europa analog in another system, we really would have no shot at characterizing any life that existed in the subsurface. But I don't think we've answered whether that's because the planet is too small or whether there's too little communication between the subsurface and the surface. If it's really the latter that's holding us up, then there's no shot at detecting. If there's no communication, you're not going to see the biosphere. If there's communication, and the problem with Europa is it's not holding on to the atmosphere that would retain that communication, well, then we've got a shot if we find a super Europa elsewhere. And it doesn't necessarily have to be a moon. It just has to have enough tidal energy to maintain a liquid water. So I just want to throw that out there. Right. Not that was Steve's point, but it's related to this whole outer solar system as an analog for extrasolar planets.
Definitely a point that's close to my heart. I worry that your super Europa may be more akin to a super Ganymede. Somewhere between super Ganymede and super Earth, maybe a sweet spot, though, where that kind of detection is possible. And I'm wondering how that factors into whether you can see signatures of what's happening in the deeper interior. What are the mineralogical aspects to tell you if plate tectonics is occurring, if there's a metal core? I doubt those sort of things are directly communicated to the atmosphere, but I don't know. Venus and Earth are definitely two different planets that have atmospheric signatures of what their interior are doing.
You would definitely know better than I would, Steve.
Fair enough.
So make sure that's in there, I guess.
Sounds like fast typing.
Taking notes.
So Glenn has another point in here. In addition to advances in observation and detection capabilities, we need advances to deal with the large data sets, statistical analyses, computational models, data mining, analysis technology, et cetera. Yep, that's one of, I think, the big priorities is, data retrieval and data assessment. And that's something that we're really just getting started on. And if you're interested in that, there is some preliminary work on gas giant spectral analysis. So we've got some spectra already of exoplanets, but no one really thinks the planets that we've got spectra for are habitable. The closest thing is probably Gliese 1214b, which is a planet that has a few times the mass of the Earth. I don't remember exactly how many times the mass of the Earth GJ 1214b is, but that's probably the most habitable exoplanet we have a spectrum of, and I don't think anyone thinks it's habitable. At any rate, we have spectra. People have started to analyze those spectra, and they've started to do it with somewhat automated tools that try to get at the most statistically likely atmosphere that would explain the data set that we have. So the people are just starting to do that work. We need to improve the self-consistency of those techniques. We need to ramp them up in terms of their spectral resolution for when we get higher resolution spectra, stuff like that. So we're doing it, but as a community, but we're just getting started.
And then Alex is just raising a question about distinguishing between pure icy and icy with substantial amounts of organic matter in it. Can we do that?
Alex, do you want to elaborate? Are you on the phone?
Should be. The line's open.
It's basically towards you. I mean, you brought it up about the exchange between. Imagine you have super Europa. You said, right? And there's some exchange between subsurface biosphere with the atmosphere. But to the very least, you would have to have some exchange between water with the surface ice, right? You have to have a migration. There is such transfer material in Europa. But I just don't know how sensitive a technique is albedo changing. Is there something spectrally from reflected light which you can say if you have substantial amount of organics in ice, whether you can distinguish one versus the other? I just have no clue what that is. I'm just educating myself.
This might be a case where you wouldn't need that atmosphere, right? Because the signature is embedded in the surface.
So John Rummel just said organic, salt, etc. are all detectable. John, you want to elaborate?
Oh, no. If you take a look at the spectrum of, if you look at what we get reflected off of Europa now, we have Tom McCord and his instrument, showing high salt concentrations in different places. Pure ice is white. And now we, of course, have got, Dawn headed to Ceres, where there's some really intriguing recent observations that suggest that it's going to be much more variegated than we might have hoped.
So is there a strategy for the exoplanets as well?
I think Alex and John, you guys should do this.
I think Alex, were you making a point again?
And Alex, can you speak a little louder? The mic isn't picking you up very well.
Well, I'm just saying. So, is this a legitimate strategy for exoplanets as well, in some kind of future if you will be able to study albedo of that exoplanet, will you be able to see those features? I'm just curious. It's such a small signal that it's not a viable strategy at all to see if you have any kind of organics in that frozen planet.
That's a good point. There would be little atmosphere to have to go through, right? Some of these.
Right. So you have an icy ball, your atmosphere is frozen out, it's not habitable on the surface, but you have, if there's something in the subsurface, presumably there is always migration because there is always sublimation of ice, always transfer of ice from equatorial to polar regions. So you will have to bring some of the material up to the surface sooner or later. So is it possible to distinguish by albedo those features if you have organics in that frozen world? That's all.
I think it's a good idea to explore.
Ty, do you have thoughts on that?
Seems like the debate.
Nancy's point about the atmosphere being tenuous means that, you should have access to spectral features from the surface. But it's at this point, it's an interesting analogy to make to Europa and studying the cycling between an ocean and what you might get up to the surface. How it might change chemically as it transits to the surface, and then what the radiation environment at the surface does to those chemicals, and whether or not you could interpret those. These are all really interesting questions.
Well, and I think this is where being able to detect a magnetic field remotely factors into habitability. I think this came up in a previous discussion, whether we should consider detecting a magnetic field as something that's relevant to habitability. I think both from the standpoint of the Earth analogy and also from the standpoint of the Jupiter system analogy, the Jupiter system being one in which the magnetic field is a driver for irradiation of the surface. Habitability would be a really relevant thing for astrobiology.
Does Steve talking?
Yeah, that was
me. Yeah, that was me.
Yeah.
Okay.
And more broadly, I think we have to go beyond the water and think about things other than the presence of liquid water, and specifically beyond the presence of surface liquid water as concern on habitability. We want to know more than just that for the cases of where there is liquid water, and we also need to consider other possibilities, things that could impact life. Alex, I think the answer to your question is that we got from the panel is theoretically yes, we could look at this sort of thing. Practically, I think you and John should look at that and find out what the answer is. See how big a spectral signature we could get from the surface, how deep that feature is, and how broad it is, and how that matches up to proposed instrumentation.
Well, I'm not a spectral guy. I just know how quickly organics can be degraded in the ices or in the soil, depending on the flux of radiation. That's possible to estimate, but you guys.
Well, then you should feed some data to Nancy or Ty, and they can make the spectra for you.
Right.
We will seek out the appropriate experts and engage them in this question.
Yeah, we'll have, as you pointed out, John, we'll have some good data from series to base things on.
Okay, last 2 or 3 minutes of the webinar. Are there any other points that people want to chip in? The document is now open for commenting. If you've got it open at the moment, close it and reopen it, and you'll then be able to make your comments. But any other last thoughts before we move on? Steve appears to have found the applause button. I didn't know there was one. Well, that's good.
Oh yeah, there's quite a few little commentary buttons. Smiley face.
Oh, cool. Well, we can all amuse ourselves now by...
There's no dumb comment button, though.
I'm sure it'll be there in the next release. Okay, no other comments. Thank you very much to our presenters. Please go and add your thoughts to the document. And if there are any discussion items that people want to add, so if the document is too constraining in the sense of your comments you really want to discuss more so, just send a note to support@noinnovation.com and we can open up a discussion thread for you. We haven't needed to do it so far. It seems to be that commenting directly in the document works well, but if we need greater space for developing thoughts, then of course we can set that up for you. All right. And with that, we'll just allow John to finish his typing, and then we will draw it to a close. All right. Looks like that's done. Okay. Thank you very much, everyone.
Great.
Cheerio.
Everyone.
Bye-bye. Bye.
Thanks, everybody.
Bye.